Voy a iniciar.
Ah,
pero
yo
sí.
lo...
Y ahorita ya está en vivo.
No, it's an
Beber agua para
yeah, I mean, they have different
Nadie.
service pins, you know, there's a
¿Qué
general,
me
but
lleva?
this
¿Dónde
is what
es?
you
Ellos
get.
dicen que están esperando que ustedes se estén para acercarse a coger.
4 para los
Son tres. Y una más para mí. Una para mí.
Big diamond, or I don't know.
Yeah. I'm just writing a note back to James. And then
Okay, yeah, go ahead, no let me distract you. Dame los materiales, yo te digo que dame las cosas que tienen que firmar. Bueno, cuando aparezca se lo entrega.
Si esta es una copia adicional que usted tiene, es lo mismo.
Es lo mismo, pero aquí ya está el pura.
Y
Porque esta la saqué de la impresora mía. Entonces esta es la, no sé que esto hay que firmarlo también. Correcto. No se me olvide. You saw the defiance paper, right?
yes, I've been meaning to actually. Jim Salas, actually president of SBM, actually tweeted it out for us. Which is great.
Oh, really? Oh, cool.
Yeah, that's cool.
Se ve muy, ¿ah?
Tome la foto.
Muy bonito, hay que tomar un retrato antes que la gente
Tres días dedicados a eso.
Ah, wow. Lo que tienes que hacer es sacar un segundo doctorado. Solo estábamos hablando ayer de que uno dice que este es el único doctorado que te ganas en Taekwondo y que te lo ganas bajándote ahí. By the way, this is Cesar's mom is here. She's connected over to Defensa. And Cesar's wife, right? And Eric is a member of his committee. You probably have heard from him.
Está presentando al profesor miembro del comité.
Él es miembro del comité y fue él es el director del proyecto en el cual Cesar ha estado envuelto también. Ha recibido apoyo. Just let him know about it. Huh?
Super young, you're super
You
young.
look very young.
Yes, you are true. That is true. I am young.
Matt's birthday is on Saturday. Actually, he's not going to come because he's got his birthday on Saturday. He's turning 40. Huh? And so,
Wait, Matt's not turning 40. Matt Boomin?
no, Matt Pete.
Oh, okay.
But, so, I'm sorry. Yeah, let's wait till.
Yeah, that was my feeling as well. Yeah, sorry I sent a flurry out to program directors. I just wanted to find.
No. The only reason I'm asking is because since I just was curious as to whether one of our other notes went to Rick or whether you actually wrote to Rick.
I wrote to Rick directly.
Okay, got it.
After I got that, and then yeah, I knew James was moving to PMI, like you know.
Yeah.
So that didn't surprise me, but still, like, well, we need to find a new person.
Yeah.
So,
Yeah.
and I also, as you know, I sent Liz. So, But just, more since Rick is more of a friend, I was just feeling like he
Yeah, no, definitely, and yeah. You know, the thing too, in fact, I showed this to Muhammad yesterday, because, I don't know, I didn't warn you about this with Muhammad,
I would say, I saw I've been reading Cesar's dissertations.
Yeah, exactly, no, yeah, so take a look, because I've already taken a look at it, I've gone through a few things, and, and stuff, so I'm pretty sure there'll be things that will, and he sort of borrowed, a little bit from the proposal and some other stuff. But anything I was showing to
it's also neat to actually read Cesar and see all these snippets from our writings. Like,
oh, really?
Put it back in together. It's like, there is an argument in compelling thinker. This is great.
Yeah. So there was some bulletin from, I guess, the American Society. It was from something I received, one of these daily blogs. And, it said that all this extra money that NIH is getting, this $1.5 billion, was stipulated on a percentage acceptance, no lower than 20%, and more early investigator in NRSA.
Oh, interesting.
I mean, I can forward it to you, whatever, but it's like, so this is supposed to be the mood in Washington and whatnot, and, what the heck, we're having, I think we're having bad luck,
honestly, I mean, I don't totally agree with the study that we're going to do, but the stuff, I was thinking through it all yesterday.
It's ready.
Okay.
I was, we'll talk more about
Yeah.
that. But the study that I wrote to you guys an email about, I mean, I think, I can't imagine that. Because now we're like full on doing the trial that people would expect us to run as an ROI. We're basically saying the system ID doesn't matter.
I know, I'm surprised that it's so early given me. Normal schedule.
We can talk more, but I wasn't really, I don't know totally with the thing is, I'm thinking right back, if I don't want to create a situation, he is he's a good collaborator, he's one of the few people with some back and actually really make it, I think he's written. You get it? Hey, hola, ¿cómo está? And, but I think some of the other people should step up, if they really feel that, this is not clear or whatever.
Ready?
Say something about
Yes.
it.
Well, a little bit nervous.
I can't. That's really true.
Yeah, exactly. That's why, again,
It's basically like beyond me. It's sort of, I think most people should really have it. It's just like, it's behind you, then it's a problem. You could help us know.
Yeah, and there's things that can be done, but, what are, these are like,
You like running?
this is like, sour cream, I guess, maybe butter. It's como cream cheese, butter, cream cheese, and
Está bien, igual.
This is happening in 30 minutes. Okay. I'll be there.
oh,
Alex,
hi,
you
you
did
are.
get here in 30 minutes.
Hi, how you doing? Yeah, get to see you face to face.
I'm glad you made it, Alex. I think this will be really valuable for you. So, sorry that I did not emphasize everything.
Grab a plate
This is
and
good
work
to see
your way
you.
down.
Good to see you in person. I'm gonna call from the psychiatrist.
Ay, te pongo, Bueno, dile que
Falta un minuto, pero
How's moving?
No, mira, mándale un mensajito, sencillamente dile que todavía estamos esperando. Porque para ponerlo, o si quieres, Porque no estábamos esperando que no llega más pizza.
I guess now.
That's actually what spurred it. I was like, you should come to the secretary. This is why I'm here, obviously. So,
How long is this?
usually he'll present for anywhere between 45 minutes to an hour.
Oh, okay.
And then we that's usually for 30 minutes. About 50 minutes. The committee commiserates, and then we're done.
I thought for some I was thinking.
justamente ahí está ya.
I'm going to be over the break area. The brickyard is over there at the base of the other side.
Okay, cómo no, cómo no.
Hang on there. Yeah, the brickyard is actually the, where the computer science,
Oh, okay.
but you're an engineer.
Yeah.
How's the presentation?
Oh, thank you, finally.
It's kind of messed up because of the
Okay, it's okay.
But it's okay.
Anyway, thank you very much, appreciate it.
Can we meet on Thursday then? Or
Okay,
regular
yeah,
time?
sure.
You have a meeting at 1, right, on Thursday with the...
You know, like, I think.
You said that in your email, I guess?
No, I have one, it's at 10.
It's at 10, okay. All right, so Thursday at 10.
Yeah.
All right. I need to see Mohammed after this.
I kind of feel like we were kind of curious about but like,
Probably no internet.
I met Matt yesterday.
half people, like, some people
Here,
can get
fine.
like me and Emma both to kind of choose in the room, but some of us just play that. But yeah, I mean, I think I did well. I think we just, I think all of your development was rushed to like present, but that's probably like, yeah, I mean, I felt like, I mean, there's clearly like, I thought it was like the group that was, that we had reviewed, so it wasn't the other early career group, but the one that had the that group, they did it. That's my opinion, was that they're just the best.
I'm gonna start it. He's ready.
Nice.
Just to set up.
I thought ours came together pretty well at the end. Me, yeah, I was happy.
We're trying Matt and I, discussed.
Hi, Professor. How are you?
I think that presentation.
Doing well.
But I think you guys really.
Ready to go, yes.
Do something.
We're still waiting for a committee member, okay? So, until he shows up, we can't start, okay? So, do you just want to wait, or you just want to watch the scene, or what do you want to do? Okay.
I don't think our presentation.
Okay. And you got my message,
It's
right?
just, you know,
I sent you a message.
I think it was. Like, it was
Yeah, an email. Yeah, like on Sunday or something like that, and then I asked you to set me up on the Skype as well.
I was. It was.
I think I did it.
really hard.
You have to give me. I sent you a contact request.
Like anything less. Like notebooks.
I don't know. There should be one from me because it was just Costas.Sakalis, right?
I was weird because it just.
It's Constantine. But it's the one he sent.
Yeah. Well, that's the one Yeah. Okay. That Costas.Sakalis is okay. Let me go ahead and resend it then. Huh?
It might be another one.
Yeah. Okay. Let me go ahead and resend it. Okay. Hey, hi. How you doing? But yeah, once Matt shows up, we'll go. Oh, you're here, Matt. Okay. Oh, you're here. Okay, great. Okay, where? I thought he was going to come here.
I feel like, you know, I think
Okay, well.
ended up working pretty well with everybody else and we like got to know each other. So,
Okay.
You and Laura do.
I don't know.
Thank you for this is really good.
You're welcome. Thanks to my mom and my wife. You're missing a nice breakfast, Professor.
You know, if you have a committee here, let's go ahead and just grab some stuff and then we'll get started. Okay. I don't know why these guys aren't here. Maybe because they worked so hard with you last night. Were you waiting for anybody else?
No. Oh, a couple of friends, but they didn't confirm.
Considera más si se puede sentar. O sea, que es un quizá. Sí, claro, no. welcome. We're here for the dissertation defense of Cesar Martin Moreno in electrical engineering, and I'm the chair of the committee, Daniel Rivera, and other members of the committee are Professor Eric Heckler from School Nutrition Health Promotion, Professor Matt Teague from Mechanical Engineering, and on Skype we have Professor Kostas Saklis, who's participating remotely. He's in Greece right now, and it's, what time is it in Greece right now?
It's 7 o'clock in the evening.
7 o'clock in the evening. Okay. So I'm very, very happy to be able to chair this defense. I will say that there are so many things in the academic life that can be stressful, but this is not one of them. This is actually a very, very happy day when you get to have a student talk about the things that they have worked on for a number of years and present their body of scholarship and get the right to call themselves doctor. Okay, so what I will do, and this is usually our tradition, is Cesar, if you could begin your presentation, and before you do so, if you could just tell us a little bit about yourself. I know you have some relatives here, and then you can get started with your talk. Oh, and then, just to be clear, Cesar will have a seminar that is open to the university community. There will be an opportunity for questions, and then the audience will be dismissed, and the committee will have a closed session. Okay.
Okay. Thank you very much, Professor Rivera. Thank you, everyone, for being here. I'm Cesar Martin. I'm a proud husband and wife. Husband and father. I'm a little bit nervous at the beginning, I'm sorry. Just to make a brief summary of my academic and professional life, I had the opportunity to work in the industry in a beer factory for 10 years, and that's the place where I acquired my passion for control systems. After that, I started my academic life. I have a tenure position in Escuela Superior Politécnica del Litoral in Ecuador, my original country. And I did my master's here at ASU in 2003. Then I went back to my university, and then sent me here for 4 years to have the opportunity to have my PhD degree. I'm very grateful, especially with Dr. Daniel Rivera, for being so supportive these 4 years, with my committee members, and of course especially with my wife and my kids that are not here right now, and my mom that is present, the rest of my family, and all my friends. Thank you very much for coming, and I'm going to start the presentation. So the title of my dissertation is a system identification and control engineering approach for optimizing health behavioral interventions based on social cognitive theory. I'm going to present a brief outline of my presentation. I'll discuss first some motivation aspects. Then I'll present the research goals and the contributions in the dissertation. And then I'll start with the core things about the work. First, I will talk about the dynamic model of social cognitive theory that is the basis of our interventions. Then I'll talk about some the aspects behind the design of system identification experiment. And finally, I'll present aspects related to the closed-loop behavioral intervention using HLPC. Finally, I'll wrap up with a summary and future work related to this dissertation. I have to say that this presentation just summarizes the most important parts of my work, but in the printed version, you can find a complete detail. So let's start with some of the motivation aspects. Nearly 50% of all deaths can be attributed to behavioral problems, particularly physical inactivity, poor diet, smoking problems. They can yield to many chronic diseases like cancer or cardiovascular problems. Control system engineering principles have been applied before to these behavioral settings. Here I have some references to past work that have been done in our lab here at ASU, specifically the treating problems with gestational weight gain, smoking cessation, and fibromyalgia pain. Intensively adaptive interventions, it's a behavioral medicine term that it's used for the treatment that can be applied to treat these problems. In our in our approach, these type of interventions can be designed when we integrate these three fields. Behavioral science with specific theories, for example, the one that we are using, SCT by Bandura. Human-computer interaction, because our signals are going to be delivered and gathered using smartphones in this specific case. And of course, control system engineering. So our interventions, finally, in the closed loop, can be designed using advanced control ideas, such as hybrid model predictive control. These are some of the research goals that we had at the beginning of our work, and we have been developing and augmenting them. Our first goal is to obtain a useful predictive model based on behavioral theories that can represent the dynamic nature of human behavior. I'm going to talk about this in details later. This is going to be all about the social cognitive theory. When we have a framework model like SCT, we now design informative and optimized system identification experiments that are going to be implemented under strict clinical constraints. And when we have a model and the parameters of the model, the next goal was to design decision policies for these behavioral interventions using advanced model-based control ideas. One of the challenges here is to consider the use of a mix of continuous and discrete signals that are present normally in these settings. These are the specific contributions of this work. These are the main 4 contributions that I can present. First, I'm presenting a novel dynamical system model for social cognitive theory. I'm going to describe the theory a little bit later. That incorporates also some improvements that are motivated by the physical activity problem. I'm presenting also a novel multiple input, multiple output PIMO identification test monitoring procedure whose purpose is to find the shortest possible experiment with sufficient information for system identification purposes. I'm presenting also informative and optimized system identification experiments that are designed for behavioral interventions. And finally, we have developed an intervention algorithm that relies on hybrid model predictive control ideas, HMPC, that is able to personalize the discrete level of intervention components. And one important thing, we incorporate what we call a maintenance training stage that is going to be performed through the reconfiguration of some of the HMPC parameters. Okay, let's start with the front matter of the theme of this dissertation. Let's start talking about the social cognitive theory. This theory describes human behavior as a way of self-reflection, self-regulation, and self-organization. It was introduced by Albert Bandura. The theory is described mostly in a narrative form. So here I have some of the main constructs that are presented in the theory, and I've classified them in a way that is more easy to understand for control system engineers. We are classifying them as outputs and inputs. Some of the outputs, and the examples that I'm giving here are related to the physical activity problem. The outputs are, for example, behavior itself. It's the physical activity, for example, number of steps that individuals perform by day. We have self-efficacy, that is the perceived confidence in achieving the required behavior. We have behavioral outcomes that can be positive or negative. For example, for the physical activity, we have weight loss or physical pain outcomes. These are variables that are stimuli to behavior. We are considering them as inputs to our model. We have, for example, observed behavior or vicarious learning. This is observed by watching others engaging into the behavior. Environmental context, for example, weather. And these that are going to be the most used for us in our interventions, the cues, internal, specifically external cues. These are triggers to engage into the behavior. For example, a friend calling us to go for a walk or something like that. So the narrative theory, it's represented using this fluid analogy. In this fluid analogy, the inputs are the inflows to each of the inventories. The outputs are the level of the inventories. And the interconnections represent the interrelationships between the different constructs as they are described by the theory. So we have a series of model parameters, beta, gammas, And they are constructed, as I said, trying to represent how the constructs are related. So, starting from this fluid analogy, we need to find a mathematical model. To do that, we rely on the principle of mass conservation, and by doing that, we obtain this set of differential equations. It's just the application of that principle to each of these inventories. Here we are using for the variation terms first order derivatives, but if it's required, we can use second order, and we can do that through self-regulation scheming into the inventories. And it's described in the document. So now we have a mathematical model, but we need values for the parameters, right? Before going to that point, we validated this model using a set of data as a cross-validation data set, and we take that from a previous physical activity behavioral study. For doing the cross-validation, we use semi-physical identification. The point with the semi-physical identification is that we assume that we know the structure of the state space representation of the system, but what we don't know is the value of these parameters theta p. So that's why these matrices are dependent on that. So basically the semi-physical identification used the one-step ahead prediction error of the system to find the values of the parameters, the estimated values of theta p. So as I said before, we use this to cross-validate our information with the data from these different studies. Here we have the plots, and we computed the fit of them using this formula. These are the results that we obtained. The purpose of these was trying to validate the model from using real or actual data. Additionally to this model, we have incorporated a couple of additional features. The most relevant here is that the one that is called ideal step goal range, meaning that each individual independently has an ideal step goal range where he or she responds better to the set goal. So the idea here is that, I'm going to use this figure to explain that. In our approach, this is based on the goal attainment. What is the goal attainment? And this is measured daily. If an individual has a set goal and it performs a certain number of steps, the goal attainment is the difference between those two. So the goal attainment is positive if individuals achieve the goal and negative if they don't. So when the goal attainment is positive, this goal attainment is feeding what is called self-efficacy. So when the goal attainment is positive, the self-efficacy is reinforced and the individual basically follows the set goal. But when the goal is too ambitious and not doable, the goal attainment goes negative and the self-efficacy is affected, and that makes this negative or inverted U response that we are observing here. So we model that by incorporating this signal goal attainment to the self-efficacy inventory, and we're going to see that in a little bit more detail once I show the intervention. So, as I said a minute ago, now that we have a basic model with some features added, we need system identification experiments to find those alpha, beta, gamma model parameters. So our basic structure for the system identification experiment relies in this two-stage approach. First, we are going to develop what is called an informative experiment, which purpose is to find preliminary information on the dynamics of the system, and it's going to be based on some randomized or general system ID sigmas application. Then, using the information from this informative experiment, we develop an optimized experiment that is going to be formulated as a formal optimization problem. And I'm going to show a couple of details of this one in a minute. Let me show our conceptual diagram of our system ID behavioral intervention. So we have here of the sampling time of this system is 1 day, because we have one set of data for each day. So at the beginning, the main purpose of the intervention is individuals reaching 10,000 steps per day on average per week. So every day a goal is delivered. This is the SCT model, and we are using a simplified version of the SCT model that is based on a more behaviorist articulation of the components of behavior. A goal is set, and we have here as U9 a second intervention component that is called expected or available points. This is a reward mechanism, meaning that we are announcing points, and these points can be later translated into physical rewards. For example, 1,000 points can be translated into a $5 gift card. It's just an example. So we said at the beginning of each day, your goal is this, and if you achieve the goal, these are the points you're going to receive. Then behavior is represented by the model. This is why for the actual steps. The actual steps are compared with the goal. If the goal was achieved, the points are granted. So one particularly structure that is augmented in our model is the use of this if-then block to represent this logical action of giving the points. Here we have also the goal attainment signal that I explained before as a difference between the goal and the actual steps. We also have this internal self-regulator via internal cues, and the purpose of adding this in is to have a closer connection between the actual steps with the set goals. So this is our conceptual representation. Now we can start with the design of the system ID experiments. These are some of the general design constraints that are crucial for this experiment in behavioral, as a behavioral intervention. Bounds, maximum and minimum of the intervention components, restrictions of move size, switching time restrictions, so the experiment does not vary that much frequency. And if we want to apply the intervention components one at a time or something like that, we can incorporate this late start day constraint. Speaking specifically about the informative experiment, the first informative experiment is designed as a fixed time experiment where the inputs are going to be randomly selected. But here's the first time we see the particularity of the behavioral intervention. The levels of our intervention components are not continuous. They must be taken from a discrete set of events. For example, if the baseline, let's call the baseline the normal amount of points that individuals perform without any intervention. For example, let's say 5,000 steps. That is something that normally a sedentary individual performs when he is not under an intervention. So the possible set goals are 5,000, 6,000, 7,000, up to 10,000. But no values in between, just one of those discrete values. Same thing for the points. We just can give either 100, 300, or 500 points. So we take the same probability for each of them and we deliver the signals. Of course, these, and by definition, these signals comply with the constraints described before. Let me describe briefly what is the optimized experiment. Remember that the optimized experiment assumes that there was already an informative experiment, so we have a preliminary model for the system. This preliminary model of the system we call here G. It's based on a top-list representation of the impulse response of the system. So this optimized experiment is designed as an optimization problem where we try to find the set of the inputs that minimize the difference between the actual steps and a desired shape or pattern for the behavior. So this is why this is more friendly with the plan or with the individual, because instead of giving just a random set of signals, we are giving a shape that the system must follow. One challenging part here, and this is described through this equation, is how we represent the effect of the if-then block. Because remember, the if-then block is a logical decision. So we do that through a big M reformulation that is explained in details in the dissertation, and these are the equations that are used to represent that as a linear set of constraints. The problem is finally resolved as an MIQP optimization problem. So let me show you some simulation results to make clear the difference between those two. I'm presenting here the model parameters that I'm going to use, or I'm using in the whole dissertation. These are the taus, gammas, betas that we are using as the simulation plan. And those were chosen to resemble results from a previous system identification, from a previous behavioral intervention based on physical activity. So that's how we chose these parameters. Also, we don't assume delays. We pick the environmental context signal as an autoregressive signal. And these are the levels of noise that we are considering our two main outputs that are behavior and behavioral outputs. These are results from the informative experiment. As you can see, you can observe the random shape of the goals and the points. Remember, the granted points are only given if the signals were achieved. Once we have these results, we use semi-physical estimation through ID gray and gray S for cross-validation to have a basic set of model parameters. And then using those, we develop the optimized experiment. As you can see, the optimized experiment is trying to follow this red shape. And I have to apologize because I had to change the monitor resolution, because when I use the HDMI, these were more clearly appreciated. But you can do that in there. But the HDMI is not working since yesterday. But you can observe that there is less variability in the outputs and in the inputs. So that's very important in terms of patient friendliness. Just as a reference, we use a different set of input-output data just for cross-validation, and these are the fits using the same formula that I showed at the beginning for the informative and optimized experiment. We can observe a slight improvement in the fit of the optimized results. However, the most important thing of this experiment is the friendliness of the inputs and outputs in the system. So, we have now this basic system ID approach to input signal design. However, in these behavioral settings, the length of the experiment is a crucial part. Remember that the sampling time of our process is 1 day. So that means that every next step that is 1 day later, we just have another point of data. So for us, it's crucial to have the shortest possible experiment, but still with identification information, with good identification information. That's how, when we develop or we enhance this technique known as identification test monitoring. So we are going to apply this over the informative experiment, and the purpose here is to obtain the shortest possible experiment and at the same time sufficient information for identification purposes. This idea of identification test monitoring was proposed before, and we are augmenting them with the use of certain additional structures. The basic is that we use transfer function computations and uncertainty computations in the frequency domain. Finally, this process will help us to understand the quality of the input-output data during the experimental execution. This is a basic flow diagram that may help us to understand what is identification test monitoring. One of the assumptions is that we have a periodic signal. So let's assume that m is the number of periods. So we start after 2 periods. After 2 periods, we compute a transfer function in the frequency domain, the uncertainties, and then we have to define a stopping criterion. That is going to be, we can use that stopping criterion based on different ideas or principles. In our case, we are using robust performance ideas. So if the criterion is accomplished, then the experiment can be halted, and we can perform the final model estimation. If it's not, we increase the number, we increase another cycle, another period, and we repeat the process. So this allows us to do evaluation of the quality of our data during the execution, on time, in real time. So in the printed board, in the thesis, in the dissertation, we have presented 2 strategies, 2 approaches for the identification test monitoring process. One that I call basic, and the second one enhanced. I'm here presenting just the enhanced version, and we have developed that in general for multiple input, multiple output systems, linear time embedded systems. So these are the possible actions. Here I'm saying that if the criterion is not accomplished, we just can increment the period. But at the same time that we increment the period, we can perform one of these 3 actions. We can add an additional period of the same signal, just more data, right? We can increment a signal with higher amplitude, or we can apply a signal with different harmonic-related frequency content. And this can may be helpful if we know something about the plan and we want to emphasize some frequency points of the signal. As I said, this action depends on operational constraints on the problem, or even in user preferences. One of the changes that we perform to apply these 3 things is the way we compute the transfer functions in frequency domain. Originally, we just used the empirical transfer function estimate method, But because if we increment the amplitude or the harmonic content, we are going to have transient responses. Now we are using the local polynomial method developed by Pinteron and all that includes the computation of these transient response. So let's start with the basic settings. Because we are going to use now transfer function computation. This is the block diagram representing the SCT model as transfer functions as blocks. These are the linear components, and this is the if-then block for the granted points that we referred at the beginning. So we are going to refer to each transfer function G from the input n to the output m as the total transfer function from each input to each output, including the if-then block. Okay? Let's start with the input signal design. We rely on multi-sign signals that are very popular and very used in system identification settings because they allow you to specify a specific or to specify the power of each frequency point into the spectrum. And this is done by the selection of this coefficient alpha. Please notice that each input now has two arguments. It depends, it's either the input 8 or 9 points or goals. But now I'm using this L symbol. L symbol is a signal in the sequence. And why we have now different signals in the sequence? Because now we can have three different types of signals. So capital L is the total number of signals in the sequence. And non-capital L is each specific signal in the sequence. For example, L equal 1 could be more signals with the same content. L equal 2 could be signals with higher amplitude, and L equal 3 could be signals with different frequency content. So ML is the number of periods in the signal. This NS, non-capital NS, is the total number of frequencies that can be excited. So how we develop these two possible variations? Change of the amplitude is very basic. It's just maintaining the magnitude of the signals within the bounds of the intervention. And if we define bounds for each one of the specific signals, then we have to make them according to the general bounds of the problem definition. The thing that is a little bit more challenging was the design of the change of the harmonic frequency content. The thing is, here we need to complete two things. Number one, we are needing frequency domain estimates. So for doing that, we need signals that are designed orthogonally excited in frequency, what we call a zipper spectral design. That means, and please observe this graphic, here in red we have U8 and in blue U9. That means in this graphic, these are the alpha, the Fourier coefficients of each signal. These are the frequencies. So if one input is excited at one frequency, the other one is not. And that happens alternately in the whole spectrum. That's what is called zipper, right? Because if one signal is excited, the other is not, right? It's like a zipper. However, if we want to also include harmonically related changes, we need these signals related by a power of 2 from the number of samples for each frequency. Meaning that if we lost 2 here, then we have 2 present here, and then we lost here in the other 2. So it's an harmonic relation. The red ones in the second plot is related harmonically to the first one. So to do that, we define what is called the harmonic reduction step, meaning that this is the original, just zipper definition of the inputs. These are the same inputs, still zipper, but with one harmonic reduction step. So they are related in a frequency of 2, and this is the second harmonic reduction step. So this is performed by selecting the coefficients alpha using this relationship that is designed to give this type of spectrum. Of course, we have here 2 total number of inputs. Well, we have now our signals. We have the possibility of 3 actions, nothing amplitude incremented or frequency content modified. Now we need to compute the transfer functions in frequency domain. As I said before, we rely on the local polynomial method. The local polynomial method has many variants and different ways of application. Here I have summarized one of the ones that I'm using. However, I'm using 2 other variants that are described in the thesis. This is called the periodic LPM, the periodic local polynomial method. the basic way to understand the LPM is that in frequency domain, the outputs are defined by the effect of the transfer function, the linear transfer function, and the input. This term T represents the transient response, and this term B represents the noise response. So as an spectrum, we see that in what we call the excited frequencies, these are the frequencies where we have an alpha defined, okay? The specific periods, and harmonic periods of the signal. We have the linear contribution and the transient and noise response represented by the green line. But in the other frequencies, where there is no points of excitation, we just have the transient and noise response. So that's why we compute this in two stages. First, at the non-excited frequencies, and actually it is in the excited frequency, for example, at this frequency, you use a neighborhood of frequencies around this here and this here, around the excited frequency. And we assume that the transient response can be represented as a polynomial because we assume that the frequency response is smooth in the frequency domain. So that's what is called a polynomial method because this is the main assumption. It's defined as a polynomial. So by using this assumption, you can see that here, because it's the non-excited frequency, we don't have transfer function terms. We find an estimate of the transient function and noise response using a linear least squared approximation. We also get an approximation or an estimate for the covariance metrics of the estimation. So basically what we do is, at the excited frequencies, we take out, this is the measurement, we take out the estimate of the transient and noise response, and we obtain a transient and noise-free estimate of the response. That it's only defines only on the transfer function and the inputs. Then, at the excited frequencies, we use again the empirical transfer function method, the ETFE, for getting the transfer function from input N to input M, and this formula to obtain the sample variance of the estimate. So we have transfer functions, we have the sample variance. Now we need uncertainties. This is the frequency grid. As you can see, this is just a representation of the formula that I used before for the Fourier coefficients. So the idea here is at each of these frequencies to find a circular region defined by the additive uncertainty that can be found with a prescribed level of accuracy that we call rho. This is the formula that we use for finding the additive uncertainty bound. But remember that this is for each element, input-output element, meaning from input N to output M. So to generalize this for a MIMO system, we rely on maximum singular values of the total transfer function, including all directions, all elements, and we define that with a probability 1 minus kappa. So we can relate the individual or independent additive uncertainties by using the Frobenius norm. And because, remember, by the simple definition, each input in frequency is independent to the other, these are independent events, so we can relate the rho's levels of accuracy that we compute with the kappa levels by using this form. We have uncertainties. Now we need the stopping criteria, right? That's the one that we need to stop or halt the experiment according to the identification test monitoring proposed. So for doing that, we rely also in robust performance ideas. This is just a brief summary of what we've done. We assume a closed loop representation. We assume the additive as an unstructured additive uncertainty that is bounded by a value LA. And according to the H infinity performance requirement developed by Morari and Zafiro, this is the condition based on sensitivity and a weight function to achieve robust performance. So by replacing this with the estimates of the sensitivity and the complementary sensitivity transfer function, this condition is transformed here in this one. To find these sensitivities and complementary sensitivities, we use an IMC, internal model control representation for the controller C. These are the basic formulas, and these are to guarantee the properness of the response. We augment this with these filters, and we augment here the use of these constants lambda that are incorporated here. Also remember that the transfer function G is decomposed in a minimum phase and non-minimum phase representation. Changing this is our robust performance index, we label it as an RPI. And the robust performance condition is this should be less than 1 for all the frequencies in the group. About the lambda parameters, these are found using this iteration because these are basically tuned elements of the controller. So the idea is to find the values that minimize the maximum robust performance among all the frequencies, indexes. Because these results are for each signal on the sequence, we can have an aggregate response of everything if we incorporate all the L elements or all the L signals in the sequence. To do that, and using basic optimization ideas, we know that the transfer function estimates using a weighted approach that minimizes the variance of the total estimate. It's going to be used if we use these inverse variance as the weights. So this is the total aggregate transfer function using all the signals in the sequence, using the specified weights, and this is the total variance. With this total transfer function and this total variance, we recompute the indexes, the uncertainty bounds, and those are the ones that we are going to use in our robust performance criteria. So with that, we have this stopping criteria. Stop the experiment after n periods if the index is achieved during a predefined number of iterations, continuous iterations that we call NMI. This is a variant that we are using for our physical activity problem. Sometimes transfer functions are not the same, and this is because we have the if-then block, right? So the if-then block may cause that the transfer functions are not the same when we perform one change in the input. So to do that, we obtain an approximate aggregate robust performance index, and we use as a weight the inverse of the additive uncertainty estimate. And we differentiate that from the exact one by this tilde set. Let me show some simulation results of this identification test monitoring procedure. In this simulation, using the same model parameters, these are not the only change for the formulation, but the same levels of noise. We are not assuming changes on the input signal content. It's just more periods of the same signal, okay? So this red line is the test bound. Remember, the test is achieved when it's less than 1, right? So when the test is achieved when the point is below this red line. And these are the cross-validation fits. So according to this criterion, this is the stopping point if I define the number of consecutive iterations as 2. If the test is achieved in 2 consecutive iterations, we can stop this, and this is achieved after 12 cycles that represent a duration of 216 days with 39.5% of accuracy of figure. The next plot helps us to understand a little bit the effect of the other type of variations. Blue one is the same as I presented before. Red is increments of amplitude. This is the additive uncertainty itself, the robust stability test, and the cross validation. And the black one is frequent change in the fundamental frequency. So as you can see, if we increment the amplitude, as was expected, we obtain the results faster, right? So in the red one, we can halt the experiment after 8 cycles, because the test is achieved after 8 cycles. If we change the frequency content, we can halt the experiment, this is the black line, we can halt the experiment after 9 cycles. So we can see that by doing these modifications, we got improvements. And we can observe those also in the cross-validation fits. But again, there is no closed rule. We cannot say, let's do this from the beginning, but because we might have constraints, operational constraints on the amplitudes or on the length of the experiment. These are the same original experiment, but with different realizations of different type of noises. These are realizations of the same Gaussian noise, 10 different realizations. Here again, it's the test bound, and this is the fit. And here we have an autoregressive type of noise. This is less aggressive, and this is more aggressive. The main difference, of course, if we have a very aggressive autoregressive signal that also resembles an integral type of noise, we need more power from the inputs to achieve the test and to have better data. That's the main idea of this. So now we can go to the final stage of the work, that is the design of the closed-loop behavioral intervention. The main difference between this conceptual block and the previous one is that now we have this feedback line. Now our algorithm takes into account the actual step. It's not an open loop experiment anymore. Now we are going to use the actual steps. And of course, this algorithm is going to be designed using hybrid model predictive control ideas. But the rest of the signals are exactly the same. We have the same if the block, we have the same intervention component. So basically, the standard model predictive control uses a residing horizon control strategy, where inputs are computed for what we call an M-move horizon, and the outputs and the rest of the signals of the system are computed over what we call a P, prediction horizon. And of course, this requires a model to do that. However, only the actual set of inputs is applied, and then at the next step, the algorithm is run again. The basic aims for the HMPC strategy is to set point tracking for goals, measure disturbance rejection. We call the measure disturbance in this work the environmental context, and a measure disturbance rejection. A measure disturbance is possible unknown effects, noise, or even unmodeled external influences. Remember, the most important thing is our intervention components are discrete in nature. So that's why we use the hybrid formulation. And it relies on MLD, that means Mixed Logical Dynamic Structure, presented by Ben Porad and Morari. And this is the way that it's realized. This is a state space representation, but with augmented signals to represent the discrete conditions or categorical conditions in our definition. And these categorical conditions are described as linear constraints by the use of these E matrices that are called the permutation matrices. So the point is, all the discrete conditions are embedded in these matrices into the formulation. This is how our problem is formulated. The goal is to minimize this objective function by finding the optimal set of inputs. Of course, the main goal here is set point tracking, but we can impose some tracking values for the move size or for the inputs. And those are controlled or are specified by these weight matrices that can be defined as penalties to each of the components. These weight matrices are defined as diagonal matrices, and in our formulation, most of them are 0, except for the original one, Q, Y. Of course, we have constraints for maximum and minimums, and this is the formal way to specify the categorical nature of the inputs. The inputs only can be taken from these sets of values, not continuous values. Also, our formulation incorporates what is called a 3-degree of freedom tuning strategy. The goal here is to, instead of relying on the weight matrices as a general tuning framework, we can use this as a way to specify the reaction or the response to the required step performance. So, for example, for set point tracking, via using this filter, we can specify the speed of response just by the value of these parameters alpha r. Same thing for the measured disturbance rejection. We can specify its speed of response by the definition of this filter. And for a measured disturbance rejection, we rely on an observer and a filter that is embedded in this block, and by the definition of the constant Kf. So the constant Kf helps us to emphasize either into the model itself or into the data through the prediction error. So we can say, we can rely on one more than the other. These are actually the same constraints that I used for the optimized problem, and these are incorporated into the permutation matrices to represent the effect of the if-then block. So these constraints, these equations, are embedded into the permutation matrix. One particular thing of our formulation is the definition of the maintenance training stage. What is the maintenance training stage? When an individual has been performing the required behavior for a given amount of time, then instead of having this initiation phase, they can pass to what is called a maintenance stage, where rewards can be discouraged because of the improved capability of reach the required behavior. So we do that through this reconfiguration. First, we use this delta goal coefficient to specify if the behavior has been achieved under a specified tolerance. And this condition is to check that that has been achieved some specific number of times. So when this condition is in and we are ready to go for the maintenance phase, we do that through a reconfiguration. And for that we use the weight matrices. We use penalties in the weight matrices. Remember that I said before this matrix was 0. Now we add a penalty into unite, meaning that we penalize the use of points. So this is only performed when when the condition is achieved and we are in the maintenance phase. Let's check some simulation results. Again, same model parameters. These are the HMPC configuration parameter, the 3 degree of freedom tuning parameter. This is the now assumed set of categorical values for inputs and outputs. For inputs, these are the basic results. We are assuming a weight of 0.05. This in the white thing is the initiation phase. So as you can see, the steps are progressively incremented by the goals, and the individual in this case is performing the behavior in a good way. Goals are given and points are also announced, and they are granted if they achieve the goal, this particular individual. When the individual is within a prescribed level of accuracy for a given number of cycles, then they can enter to, or he or she can enter to the maintenance phase that is in the blue shade region. You can observe that in this phase, points are discouraged. We retire points. However, individuals are capable still to reach the required behavior. Just for simulation purposes, we enter a particular disturbance in the environmental context. So when that happens, the maintenance phase is deactivated, points are offered again, but when the condition resumes, then the maintenance phase resumes false. This graphic is just a zoom of this region, the first maintenance region, just to check or to observe numerically the performance in terms of the required points. So by doing that, I'm using two norms. So blue one is with a higher weight, and red one is with a smaller weight. So if I have a higher penalty here, then points are practically totally discouraged against the red one that has a less restrictive or a less penalty than the other one. Same for the granted points. You can observe that the goals are almost the same and the actual steps are almost the same. However, the one that has more points has less offset with respect to the desired behavior. So points still are useful, but not as, if they had a good initiation stage, they are not as fundamental as they were at the beginning. This graphic is just to compare the performance of the system against an internalized only intervention that use only internalized cues, meaning only self-regulation. So here we can observe how the individuals are achieving a better response. And for doing that, we can observe self-efficacy. The blue one is the HMPC, the black one is the one with no HMPC. So you can see by giving points, the self-efficacy of individuals is augmented. So individuals say, I can do it. I can perform the behavior. So by doing that, they don't need points anymore during the maintenance phase, or at least not that many points that they did before. So compared with the other intervention, they would need, in this case, they need internal cues. But that depends on the self-regulation mechanism that might lead to a good performance or not. Of the HMPC formulation. Here we use only parameter mismatch, meaning that we assume the structure is correct and we are just varying the values of the parameters. So we can observe, for example, if we have plus minus 50% parameter mismatch, this is the blue one again, the blue line against the red one, that the response of the controller is basically the same. But as we are getting closer to more mismatch, then we start to observe some variations in the response with the controller. So the idea here is our controller is robust up to some level to mismatches from the model and the system itself. So let me summarize the content of my dissertation. I'm not going to go to each point in detail, but just briefly in general. I have demonstrated here by our work within our group that control engineering principles can be applied in behavioral settings and specifically in the design of intensively adaptive interventions. First, we develop a human model of human behavior based on social cognitive theory, and of course based on the low physical activity problem, we have improved it with some features that are important in these settings. We propose an open loop intensive adaptive intervention for system identification design using the informative and the optimized experiment. Given the natural properties of the behavioral health interventions, we developed the ITM, the identification test monitoring technique, in order to find the shortest possible experiment, but that is good enough for system ID purposes. As we cover, these relies on computations of uncertainties in frequency domain, and those were done using the local polynomial method and yielding to robust performance and ideas that were tested. Finally, we developed a closed loop intervention using hybrid model predictive control ideas and the mixed logical dynamic framework that is within the HMPC. And we incorporate the transition to the maintenance stage through the reconfiguration of the HMPC parameters. Our main goal here, our overall vision, is to have something like this. For example, an intervention that starts with the identification testing stage, then goes to the initiation stage, and finally ended up in the maintenance stage. That's what we call in the group a perpetual type of intervention. We have done some steps right now. The group has developed what is called the Just Watch intervention at Arizona State University. Professor Eric Heckler is the head of that one. And we are in the stage of analyzing data. We are in the stage of, I have to say that those experiments were developed using the ITM, the multi-sign signals that I presented here. So we have real data right now based on these intervention designs. And we are in the stage of optimizing the system identification experiment. Some ideas of future work that are related to these research activities. One of our major goals is the development of what is called just-in-time adaptive interventions. The main difference here is that instead of giving a fixed intervention components each day, we would like to find the best moment within the day where the opportunity to engage in behavior has more receptiveness. So for doing that, we have to consider multiple time scales problems, what we call within-day interventions. And some ideas are going to be tested, like model on demand, to find the values of states in this type of intervention. Here I'm using some of the ideas that we're talking in our research group about results from the Just Walk study. For example, we need, for the next stage of this experiment, we need to improve the metrics for some of our inventories of efficacy and outcome expectancy, so we can have more variability and more continuous measurements of them. We are doing more deep analysis of the elements that are within the environmental context signal, for example, weather, busyness, or weekday. So we can, and maybe we need to add some additional dynamics to the system if it's required. Also, we got the conclusion that we need more low frequency contained for the signal, especially if we need more information from step responses. Another alternative that is also evaluated these days is the use of goal setting as a single intervention component to have a different approach, or a more simple approach that can be used further. Some ideas in the direction of the improvement of the identification test monitoring procedure. As I mentioned during my presentation, there are some variants for the local polynomial method. One of them is called the fast LPM, that it's described in details in my document. The advantage of the fast LPM is that it does not require the use of zippered signals, because as we did with the transient response, the transfer function can be also assumed polynomial, as a polynomial. So we can define from the definition independent values for each of them. The problem is normally this method is more conservative, and normally it produces more biased results. So we have to do analysis and make a trade between those two techniques to find which one is better in our setting. And finally, this work can be modularized and take part of improvement in behavioral settings of physical activity that can be considered as part of novel cyber-physical systems for medical applications that are currently under development. I'm finishing just showing a list of the publications that have been result of this research work in these past 4 years. You have that also in the printed version of the dissertation. It will be very productive. These are some of publications that are under preparation. And again, thank you very much to this institution. Again, my special thanks to Professor Rivera and my committee members for all their support. Thank you very much.
Okay, so let's allow for opportunity for questions from the audience other than the committee, since we will have our closed session. Any questions for Cesar? There'll be at least one question. Or one suggestion, you need to increase your iCloud storage. Okay, yeah, so fine.
You mentioned some future work, after the work you've done with Professor. Do you see the transition to an industry of certain applications that use your work in the near future?
Yes, of course. I think the ideas we're developing here are just the starting point for new developments that can be used in these real settings. For example, right now in the industry, you probably have seen those. The phones come with applications that give you goals and whatever, but they are mostly based on, it's like the informative version of what they want to do. So our approach is, of course, this is a long term. It's like having the behavioral scientist in your phone, right? So helping you to do this in an optimized way, in a better way. So yes, of course, we are just in the starting stage. We're just validating models. We have a long way to go, but I definitely think that this is going to be very interesting for the industry in a closer future.
Okay, any other questions?
Yes, Mohammed.
Yes, if you go to slide 30, please, 30. That's the only question I have. Yes, it would be great. Probably I'll need to go through your dissertation for details, but for your stopping criteria, it would be great if you could elaborate on the during the last NMI iterations. What is NMI? I mean,
Yes.
I couldn't follow with that.
Thank you. Yes, that's just a predefined number of iterations. For example, it depends on how long you want individuals to have achieved, or not individuals in this case, how long you have your iteration being achieving or accomplishing the stopping criteria. So, for example, and we have seen that from all the simulation. The stopping criteria could be achieved one time, but then 3 times is not achieved. So we don't call that a unstable performance. So this parameter allows you to define what you call a stable or a stabilized way to say that the criterion is achieved. So in my simulation I use 2, right? So get 2. So I said, well, if it's achieved 2 times, then it's good. But just for example, if I would say NY is 1, then I would have to stop in the first iteration. So 1 is not a good recommendation for this.
Okay, thank you.
You're welcome.
Any other questions? Okay, well, if that's the case, then let's go ahead and thank again. What we will do now is move to the closed portion of the defense, right? And so we'll ask you to be excused. I'm pretty sure that on your way out you can grab. There's still a lot of food, right?
Please take it.
Yeah, exactly. And then okay, and then the committee will ask questions.
So we now dismissed? Or
Yeah, you're dismissed. You're dismissed. Yeah. No, well, I mean, after we're done, he can contact you and tell you, yeah, you guys. Lo vemos el sábado, entonces.
I think it was
slide 34, and I was like, I like that version better. Simple stuff. I'm gonna grab a little bit of stuff.
Yeah.
I'm gonna sit up.
Yeah.
You should stretch. You can get something too if you want.
I would say after. I'm not in the mood.
You have to say a percentage of what you understood from that. So it really is. I didn't know if it was like you described programming, how you can follow it when you came in that program. So what would that be? 40-50%? Maybe a little more than that?
If I understand, that's more.
Yeah. You know, the thing you can figure out the defense and electrical. You know, so we can no, we probably go in front of Rusty Eric probably.
Oh, yeah, sorry.
It's not yet time of congratulations. Sí, gracias,
I'm
gracias.
very aware that this is going to be
Spanish
Rafael.
Yeah, I think so. I don't know. No.
Oh, that was done before his bedtime.
I'm not thinking.
Oh, okay, no.
Si ya está empezando.
That's great.
Muy rápido.
Mejor
pueden ir.
But yeah, I'll bring you something.
Yeah, well, okay, that will work, whatever. Yeah. Okay.
Yeah, but I'll be there. I'm sorry I have work.
Okay.
I put it already on my Google Calendar. That's true. Good job, Cesar.
Thank you, thank you.
Bye. Oh.
And you missed the best part.
Where do you acknowledge my work?
No,
That was a joke.
I'm pretty sure that was a joke. No, the little ceremony part, you know, that's the stuff that we only do when it's a defense. You know?
We got the Capuan thing out or something?
Yeah, the Scottish bagpipe people came over and,
And we got that crazy metal, you know, that we have?
Ready. Ready. Si quieres seguir, puedes seguir.
¿Cómo hago? Pero... Deja fuera. Venga, venga. Póngase. La estoy filmando en vivo. Diga hola. Es video. Ya, vamos. Sorry.
Then I really want to go to check it out. I've got that in my bucket list.
You're going to the lab?
Yeah.
Can I join you?
Hello.
Good job, Cesar.
Thank you.
All right. Take care.
Our meeting is at 12:30.
Yeah, already. So, yeah.
Está viendo ahí, mire. En el video, mire si está. Estoy grabando. Es que César me dijo. Se escucha, creo.
I was just trying to pull it up, right? So you started with a continuous hyperbola. What like that? Discrete?
Not in the formulation, sir, but the completion. Formulation is, even the physical formulation is a space in the
Right. Yeah, so the thing on page 7 is continuous. And then I think page 14 is discrete. And so your optimal input formulation, that's
Sale. No sale. Déjame ver.
again, with the connection with the line that
Familia con interés.
Is anything else done for you this time? The MPC is discrete.
yeah, MPC is the selector is our strategy. Because we try to find the alpha that tells us.
¿Puede tenerlo un ratito aquí? No, Sam. Es que voy para allá, al bar. Aquí, en Cesar. Es que dice que... No, sí está grabando. Está saliendo, ya lo vi. Aquí, si quiere la suma aquí o lo que no.
I wouldn't recommend to go this as the first qualification. Right? So the idea is we are doing the system identification. We're starting to gather some information every time one of the cycles is done. So the idea here is that we need to emphasize some frequencies in the system. Since we have, for example, it's like what we have here in our group. We say we need more low frequency, we need more low frequency. We can use the same power instead of distributing the power to all the frequencies. We can emphasize frequencies here. Of course, if we have the same information.
Sostén, esto cansa, oye. Es que me mandó, tú quieres que venga ahí, me mandó para este lado de acá porque ahí estaba viendo el tribunal.
¿Qué?
El tribunal veía que nosotros estábamos ahí, entonces me hizo así que me venga acá. No, ella no quiere. Ah, no. No, pero así.
Míreme aquí un ratito para ver si está grabando. No, aquí un ratito, César, mírelo. A ver si está grabando para cogerlo.
Se puso oscuro, oye.
No, está bien. Está César.
Sí, pero está
Déjame ver.
oscuro.
It's going to be better understood and used if you got some information about the spectrum.
¿Está César? Sí. Ah, pero...
No, que está como oscuro esto.
Ay, César dijo que no lo vea.
Que no haya, para que no vea.
Ya. Sí, yo hubiera sacado uno. Allá, ahí ve. No sale, ¿no? Está como... Ya.